applying properties of definite integrals. Callie's New Year's resolution is to exercise more and lead a healthier life. Good for Callie. In January, she purchases a gym membership and starts tracking her workouts. When Callie is on the elliptical, the rate at which she burns calories measured in calories per minute, Callie's calories per minute, is given by f of t, whose graph is shown below. During the first 4 minutes, Callie burns 20 calories. So as we look at the graph, during the first 4 minutes, she burned 20 calories. Can you color that? Can you shade that in on the graph that you have? And the reason why we're given that specific information is because that part of the graph is not linear. If I were to look at that part, I'd have no idea what equation that came from. I wouldn't have a way geometrically to find that area. So they're saying that during these first 4 minutes, she burns 20 calories. So the area of this region, the base times the height of those infinite number of very thin rectangles all summed up with each other is going to give us a region with an area of 20. So from 0 to 4 minutes, she burned 20 calories. That's what this is saying. That area is 20. How do I know that? Well, again, if I think about a rectangle in there, the base is in minutes, the height is in calories per minute. If you multiply calories per minute times minutes, there's going to be our calories. First question, how many calories has Callie burned on the elliptical after 16 minutes? Can you show your work? So we know we have this little region of 20 already. So can you look at the other regions and figure out how many calories she's burned after 16 minutes? There's different regions, break it up into different regions. You could subdivide it in other ways. I would recommend doing those vertical segments so you can see it over different time periods. You don't know what other questions are being asked yet. So rather than try to draw horizontal lines in there, drawing vertical is going to make it much easier to answer other questions because we can answer in terms of the minutes. The first region is a nice rectangle. What's the area of this one? 72, base of 8. Height of 9, so that area is 72. So between minutes 4 and 12, Callie would have burned 72 minutes. The next one is this trapezoid. Average of the bases times the height. The height is 4. Average together the base of 9 and the base of 15. So add them together, divide by 2. Anybody have the area for this region? 48. And let's just go ahead and keep going with the other ones. The next region is another rectangle. Base times height. The base is 4. The height is 15. If we multiply those, I know that's going to be 60. And then the last one is another trapezoid. Average your bases times your height. Anybody get the area for this last one? 36. All right, so now we have all that information. We'll see what we have to use in the various problems, but it's nice to get that out of the way. In question 1 then, how many calories has Callie burned on the elliptical after 16 minutes? The information is now on our graph. See if you can answer it. Share your idea with a friend. Show your work. You don't have to show everything. We have a lot of things on the graph, but make sure you show enough that justifies why your answer is what it is. So we're adding those different regions from 0 to 16 together, and I believe that's going to be 140 calories. question number 2. After 12 minutes, Kelly looks at her Fitbit and sees that she has burned 1,650 calories so far that day. Write an equation J of X that gives Kelly's total daily calorie burn after being on the elliptical for X minutes. So after 12 minutes of doing this, she sees that she has burnt 1,650 calories. There's question A. I want to go down to question B first because I think that would be kind of helpful for us. Could you work your way backwards to figure out J of 0? Now, J of 0 corresponds to just starting working on the just starting working on the elliptical. That doesn't mean that's the start of her day. She's done things prior to that, so she's already burned off some other calories. So if she has burned 1,650 calories 12 minutes after this starts, could you work backwards to figure out J of 0? Go and turn back to that friend again. Do you have an idea what you're doing? Let me give you just a very brief time here. Do you have an answer? Do you have some thoughts you can share with your friend? And we'll come back again.
It looks like times 92.
Oh, yeah.
That's what I think.
Plus 1.
And that's
Oh, yeah.
however much you can burn.
Oh, yeah, that's true.
1 calorie.
Yeah.
1 calorie a minute just to live.
Okay, so let's see. At the point in time, 12 minutes after she started working out on this, she's at that orange vertical line. She's burned 1,650 calories. What if we went back in time to right here, 4 minutes after she started working out? Well, we know she burned 72 calories during this time. So could you figure out how many she burnt right here? Like how many were burnt during the day up to this point? And then go back one more time to get to J of 0. Griffin, what did you get for J of 0? 1,558. Anybody else get that? 1,558 calories. So you're taking the 1,650, subtracting 72, subtracting 20 to go back in time. So she has 1,558 calories burned at J of 0, the time when she started on the elliptical. Up to that time of the day, she'd already burned 1,558 calories. Now let's go back to letter A. We have to write an equation J of X that tells us how many calories she has burned entirely at any time X. There's a couple of ways we're going to write this one. It's going to be an integral. An integral is the great accumulator. It accumulates like this rate of change for us. What do you want the lower bound of this one to be? 12 makes a lot of sense. There's another number that makes sense that we'll go to in a second, but let's go with the 12. Why 12? Because we're told information about 12 minutes. The upper bound, because it's an equation for J of X, that's why there's going to be an X up here. If I want to know J of 15, I plug 15 in for X. If I want to know J of 20, how many calories has burned 20 minutes after we started working out, I could plug 20 in for my upper bound. So X is just an independent variable. What function is going to go on the inside for this one? F of t dt. So this integral is going to accumulate all the area under the curve from t equals 12 to t equals whatever we want x to be for our upper bound. It's going to find all of that area under the curve, the accumulated number of calories that she has burned. Now, that doesn't tell the whole story, though. It doesn't tell the whole story because that would be assuming that up until this point, she hasn't burnt any. So what else do we have to add into this? Plus 1,650. So the lower bound at 12 minutes after starting, she'd already burned this. And this is kind of like a y equals mx plus b. Can you see how this is kind of like a y equals mx plus b? It's another form. The 1650 is our y-intercept. It's an initial amount. The m, what is the m? Isn't that kind of like our f of t? Like the slope, the rate of change? And then the x is like the dt, the width of each one of those. So it's kind of like that. It's also kind of like our point slope form if we want to think about like it's not at 0, it's at 12 right now. So that's one way you could write it. Based off what we did for letter B, could you write an equivalent form of this one where you use that information? Let me give you a chance to see if you can write another form of that yellow that uses the blue as a beginning point.
Yeah, it would be 0.
Dude.
Why wouldn't it just be, why wouldn't you integrate from 0 to x? Because if you take any time before 12 right now, that doesn't work. Because you're adding 1650, so I'd say, would it work? You're working backwards, right? Oh, so you have to flip it. Oh, yeah, that's okay.
All right, so lots of good comments I heard out there. This, I called it y equals mx plus b. It's really maybe more of a y minus y1 equals slope times x minus x1, because we're not starting with a y-intercept. We're starting with a point of 12, 1650, really. Like it's a point. It's not like a true starting point. Whereas for this one, we could say j of x is equal to 1558 plus, here's the key part, integral from 0 to x, f of t dt. And this would be equivalent to our yellow one, because we have when t equals 0, this is how much we had at that point. And now I could use this to find any j of whatever value I wanted to. J of 16, j of 24, even j of negative something, like time before we started working out, if I had more data that was given to us. This last one we wrote, it maybe is a little bit better because it's starting with a lower bound of 0. However, the first one we have, I didn't have to do all the calculations to figure out this 1558. So assuming maybe I made a mistake to get to this one, then this j of x with 0 as a lower bound would have been off. Again, it's one of those opportunities to make a mistake. I might as well use 12 as my lower bound when she'd already burnt 1,650 calories. Another question was asked was, what if we wanted to find j of 4, right? Like, how many calories had she burned 4 minutes after starting? It would be 1,650 plus the integral from 12 to 4 f of t dt. Notice from 12 to 4, we're moving backwards. So we could flip the integral and then make it a negative, or just recognize because we are moving the other direction, the area under the curve, this 12 to 4, I wouldn't consider it a positive 72. I'd make it a negative 72. I take 1,650 minus the 72 to figure out j of 4, how many calories she's burned up to that point. So it should work whether we're going to the left or to the right. Question 2 is the most conceptual question on this front page. 3 and 4, I'm going to have you try. I'm not going to say that they're going to be really obvious to you right away, but these are going to be more procedural, I would say, if you can think of like what that drawing is doing. I want you to try numbers 3 and 4, see if you can answer those.
get 172. Sorry.
What was your?
I didn't do it. I didn't do it.
Yeah.
I'm trying to write it. So, that's fine. 172. At 220. Yeah. It's like, cause it's the 140 versus
Yeah.
plus the 5 times
So you
the
just
scale.
scan it and you send it wherever.
Cause that 5 is essentially.
No, I know. I know where you got that part. I use the exact same part. I use the 1650 and 1558. Exactly. And I was more the same. Got married to, but it added that 5 and 16. And 8 out. And 80 plus 90. So it was just how you got your space.
All right, for number 3, let me show you 2 ways to consider this one. So the rate of burn is f of t plus 5, which means from our graph, if this is the f of t values, what do we have to do with every point that's on this graph currently? Shift it up by 5, right? So up by 5, up by 5, up by 5. Everything goes up by 5. So then the new graph would look something kind of like this. Let me clean this up just a little bit. So if I were to draw like a horizontal line at y equals 5, oops. We already found all of those little regions up there, right? All those vertical lines, we can subdivide it however we want. We've already done all that stuff. What would be the area for something down here? Because this would be our increased area compared to what we had before. It's a rectangle, base times height, right? And I went for the whole 24, so let me back up and go to the actual problem we're dealing with. So the whole thing went up again. We're only going to 16. So this region, we had all of those numbers before, plus what would this area be down here for the question we're actually being asked, going from 0 to 16 minutes? 5 times 16, so 80. How many calories did she initially burn, and what I had as the original gray area? Well, that's what we were asked in question 1, right? When we actually found this area, we said that was 140 calories, all those individual pieces, and we have to add 80 more onto that. 140 plus 80 is going to give us 220 calories. So that's one way to look at this one from a graphing perspective. The other way I could look at it, and I kind of did this with the 140, the integral of f of t plus 5 dt from 0 to 16 is the integral from 0 to 16 of f of t dt. That's the 140 we have right here. We already found that one. That was the area under the f of t curve from 0 to 16. Plus, we can split it, the integral from 0 to 16 of the 5, this 5 plus 5 dt. So this is saying what's the area under the curve y equals 5? Just the horizontal line y equals 5 from 0 to 16. That's the length of 80 that we have right there. So graphically, I can see what those shapes are, or I can split these and think about like how I'd actually calculate them. Question number 4, I would say, is a little bit more straightforward as far as like what this is going to look like. And I'm not even going to try to draw it on the graph. Go ahead and answer, or read it first. So what I have right here is the integral from 0 to 24 f of t dt. A little short turn and talk. What does this represent right now? What does just this part of it represent? And then what would you do with this to get you the 16% faster with the men burning their calories. Go. Okay, so this is the amount of calories that Callie has burned from 0 to 24 minutes, right? And we're saying that we need to get 16% greater than that. So we're just going to multiply it by 1.16. I could do it inside or outside. I might as well do it outside then. So I can evaluate all of this integral, which means from the original numbers we have on the graph, find all of that area under the curve, which was 236, I believe, times 1.16. You're probably going to want to go to your calculator for that. 273.76. So number 4 is like a little more straightforward with the calculations. We're just increasing what Callie's would have been, increasing it by 16%. So we multiplied it by 1.16. Okay, turn the page. Big box. So in these big boxes, we write just like the integral properties, some of our big findings. So we practiced around with some of these different concepts that we're going to put into a box to formalize them, and then we'll do a couple of examples. Let's see. Number 1. Probably going to take up more space in the box because I want to write kind of big. Here is our first one. And we kind of use this indirectly. We didn't talk about it formally as we're going through these problems. Notice I have the integral from a to c of f of t dt. And I'm saying I'm breaking it up. I'm going from an integral from a to b and then from b to c. I'm saying those are the same thing. What does this mean? If I want to know the area under the curve going from like this x value to the x value of 16, I could find the area under the curve from 4 to 12, and then 12 to 16, and then add them together. So I can break it up into different regions. And really, it doesn't even matter if A is less than B is less than C. They could be in any order left to right, because if the upper bound is bigger than the smaller bound, we would just be going backwards, so it would be a negative then. So we can change our upper and lower bounds as long as I go from A to B and then continue from B to C, as long as these are the same. I wouldn't want to go from A to B and then start somewhere else. I'm going from A to B. Where I left off here is where I'm picking up on the next one.
Is there a way to, I guess, kind of close it like the integral of
You mean something like this?
Yeah.
Or put it at the end. It's not bad practice. What is important, what I would say is, if I have, let's say, x plus 3 dx, I don't have to do this, but it's a good idea to put parentheses around and say the whole thing is being integrated. It's a good idea. All right, so there is our property number 1. Property number 2, we've already talked about this one a little bit. The integral from a to b of f of t dt. What happens if we change the bound? We made b go to the bottom and a to the top. So if you switch the bounds, you put a negative, you make it an opposite value, left to right or right to left. Think about that as you're working through those problems. So the question earlier, next one, I have integral of f of t plus g of t dt. So I have 2 different functions on the inside. They could be complicated functions. They could be simple functions, just like adding a number in there. I have a plus sign in here. Well, plus is just like, or negative, subtracting is just like adding a negative. So I could have a minus in there just as easily. And we did this on the last problem and in a few others. What can we do? Well, we can split it, dt, into two different integrals. So instead of doing like the whole sum at once, I can find the integral of the first part, find the integral of the second part, and then add them together. I don't have to try to think about doing it all at the same time. Number 4. This is number 4 out of 5. Looks like this. What does k represent? A constant. What do you think we can do with that constant? Push it up front because why not? Makes the integral a little bit easier to do. And it is a constant. It's not like a function of something. I can't put an x out front or a t out front. I can't put a variable. I can't put like a cosine out in front. It's only if it's just a number that's inside of there that we can push it out front. And the last one. There's more like kind of what I consider basic rules of integrals that will come second nature to you later. But here's our first 5. And here's the last of these 5. The integral of f of t dt from a to a. Now think about that, what that would look like graphically. The function f of t could look like anything. But it means find the accumulated area under the curve from t equals a to t equals a. So the answer would be 0. If upper bound and lower bound are the same, there's no rectangle there. It has no width to it, so it would be 0. Okay, so 5 different rules that will become second nature to you. Of these 5, number 1 is the only one that can cause some confusion with changing the bounds. The other ones will seem like, yeah, okay, 2 we've already done. 3, of course, we can split them. 4, put the constant out front. And if the upper bound and lower bound are the same, the area, the integral is 0. Okay. Number 1, parts A, B, C, and D. You are given all of this. From that, we are asked 4 questions. So ask questions about F and G. The bounds are changing. Some of the bounds aren't quite in the given. So we have to figure out how we can use that yellow given information in order to answer these questions. So we'll call those facts 1, 2, and 3. Which one of those facts are going to help us in this question A? It's dealing with f of x, 7 to 9, so we're going to use number 2. Now, they're not the same, right? What is this answer going to be for us? Opposite of that, so the answer would be positive 5. Because the bounds are switched, the bounds are switched. The answer is switched. Letter B. Which one are we going to use for this one? 1 and 2. We need to go from -3 to 7. Well, for number 1, we can go from -3 to 9. I didn't want to go all the way to 9, but this one's like, think about like a bus stop. I'm going to go past it. Then I need to go from 9 back to 7. So this integral is going to use number 1, going the integral from -3 to 9, f of x dx. That's equal to 8. How are we going to use number 2 then? Because 2 is going from 7 to 9. we want to go from 9 to 7. So the integral from 9 to 7, the one we just found, right, over here, plus the integral of from 9 to 7, f of x dx is 5. So we have 8 plus the 5. We add those integrals together, 8 plus 5, 13. Okay, next one. Break it up into pieces. There's a plus sign in between those. What is the integral of f of x from -3 to 9? Plus 2 times. What's the integral from -3 to 9 of g of x? 11. So we're going to multiply it by the 2. 22 plus 8, we're going to get a 30. And last one, letter D. The integral from -3 to 9 of g of x would be, that'd be 11. And then what's the integral from -3 to 9 of -2 dx? And if I wanted to, as far as constants go, I could push the negative out front and keep the 2 on the inside. So think about a graph where the function is y equals 2, going from an x value of -3 to an x value of 9. You're looking at the area between this horizontal line of y equals 2 and the x-axis. What kind of shape is that? It's a rectangle. The width is 12. The height is, so this integral is the minus out front. So -24 for that part. Answer is -13. All right, so make sure that you have the Khan Academy done for tomorrow.